Welcome back to Math Kernel. This is the full exercise set for the scalar product and the norm, 12 problems that together cover every case you can be asked. We do the two ways to test positive definiteness, the parametrized version, scalar products on weird spaces like matrices and functions, the complex case, norms and distances, and 3 short proofs. Every step is on screen. Pause whenever you want to try one first. Problem 1. The form X transpose My, with M the matrix 3, 1, 1, 2. Is it a scalar product? Walk the 3 axioms. Pause and try. The reflex, 3 axioms, in order. Bilinear, symmetric, positive definite. Write the form down and march. Axiom 1, bilinearity. It's a matrix sandwich, X transpose My, so it's automatically linear in each slot. Free. Axiom 2, symmetry. Is M equal to its transpose? Mirror the off-diagonal, the 1 and the 1 match. Symmetric. Done. Axiom 3 is the real work, positive definiteness. Expand the quadratic form, 3x1 squared plus 2x1x2 plus 2x2 squared. Standard move, complete the square. Pull out the 3, complete in x1, and the cross term is absorbed. 3 times x1 plus a third x2 squared plus 5/3 x2 squared. Both coefficients, 3 and 5/3, are positive. So it's a sum of non-negative pieces, at least 0, and 0 only when both squares vanish, forcing x to be the 0 vector. That's positive definiteness. All 3 axioms hold. It's a scalar product. And the picture is the bowl. The quadratic form opens strictly upward, never below the floor. Problem 2. Same setup, new matrix, 1, 2, 2, 1. Is it a scalar product? And if not, don't just say no, prove it. Pause and try. The matrix is symmetric, 1, 2, 2, 1. So the first 2 axioms sail through, bilinear because it's a matrix form, symmetric because M equals its transpose. If you stop there, you'd wrongly pass it. Everything lives in axiom 3. Expand, x1 squared plus 4x1x2 plus x2 squared. That large cross term, 4, is the warning. Complete the square, x1 plus 2x2 squared minus 3x2 squared. A minus sign, a difference of squares. That's a saddle, not a bowl. Now the mark-earning move. Don't just claim it fails, hand over a witness. Kill the first bracket with x1 plus 2x2 equals 0. Take x equals minus 2, 1. The form is 0 minus 3, negative 3, below 0. A negative length squared is impossible for a real scalar product. Positive definiteness fails, so it is not a scalar product, proven with the concrete vector minus 2, 1. Always name the witness. Problem 3. Completing the square in 3 variables is painful. So learn the exam's favorite shortcut, the Hurwitz or Sylvester criterion. Here's a 3x3 symmetric matrix. Is it positive definite? Pause and try the minors. The Hurwitz criterion. A symmetric matrix is positive definite exactly when all of its leading principal minors are positive. The leading minors are the determinants of the top left 1x1, 2x2, 3x3 blocks, and so on. 3 cheap determinants instead of completing the square. Our matrix is symmetric. You can read that off the mirror across the diagonal, so the criterion applies. Now just compute the 3 leading minors. D1 is the top left single entry, 2. Positive. D2 is the 2x2 top left block. Its determinant is 2 times 2 minus minus 1 times minus 1, for minus 1, 3. Positive. D3 is the full determinant. Expanding along the top row, 2 times the minor 3, minus 1 times the little 2 by 2, which is minus 2, so 6 minus 2, 4. Positive. All three leading minors are positive, so the matrix is positive definite, and X transpose MX is a genuine scalar product. On the exam, this is almost always faster than completing the square. Reach for it first. Problem 4. A parametrized version the exam loves. The matrix depends on a parameter t. For which values of t is it a scalar product? Pause and find the range. The matrix has a 1 on the diagonal and the parameter t off it. Symmetric for every t, so the first two axioms always hold. The whole question is positive definiteness, and it will depend on t. Use Hurwitz again. The first leading minor is just 1, always positive. The second leading minor is the full determinant, 1 times 1 minus t times t, which is 1 minus t squared. Positive definiteness needs that positive, 1 minus t squared greater than 0, which means t squared less than 1, that is, t strictly between minus 1 and 1. Check the boundary to see why it's strict. At t equals 1, the form collapses to x1 plus x2, all squared, and that's 0 for the non-zero vector 1, minus 1, so at the boundary it's only semi-definite, not a scalar product. So it's a scalar product exactly for t strictly between minus 1 and 1. The green region under the parabola 1 minus t squared is precisely that range. Outside it, the determinant goes negative and the form turns indefinite. Problem 5. A weighted scalar product, 2x1y1 plus 5x2y2. Show it's a genuine scalar product, then measure the length of the vector 3, 1. Pause and try. A weighted product. Each coordinate carries its own positive weight, here 2 and 5. Read it as a weighted sum. Verifying is quick. A vector with itself is 2x1 squared plus 5x2 squared. Both weights positive, so the sum is never negative, and 0 only when both components vanish. Positive definiteness holds precisely because the weights stay positive. Symmetry and bilinearity are immediate for a weighted sum, so all three axioms hold. It's a scalar product. Now measure. 4x equals 3, 1. The product with itself is 2 times 9 plus 5 times 1, 18 plus 5, 23. The norm is the square root, root 23. Not the ordinary length, the weight's reshaped distance. Geometrically, the unit vectors form this ellipse. 2x1 squared plus 5x2 squared equals 1, squashed harder where the weight is bigger, with semi-axes 1 over root 2 and 1 over root 5. Problem 6. Once a scalar product is fixed, it defines length and distance. With the matrix 2, 1, 1, 2, find the norm of x equals 1, 1, and the distance between x equals 1, 1 and y equals 1, 0. Pause and try. First, expand the quadratic form once, so we can reuse it. X transpose mx is 2v1 squared plus 2v1v2 plus 2v2 squared. Norm of x equals 1, 1. Plug in 2 plus 2 plus 2, 6. So the norm is root 6. Notice the ordinary length would be root 2. The coupling in m makes this vector longer. Distance is just the norm of the difference. Subtract x minus y is 0, 1. Feed that into the same form. Only the 2v2 squared term survives, giving 2. So the norm of x is root 6 and the distance from x to y is root 2. Same recipe every time. Build the difference, then apply the scalar product's own quadratic form. The metric belongs to the product, not to the coordinates. Problem 7. Vectors don't have to be arrows. Here they're matrices. The trace form, A with B equals the trace of A transpose B. Show it's a scalar product on 2 by 2 matrices. Then find the norm of a given matrix. Pause and try. The trace form pairs two matrices into a number. Transpose the first, multiply, take the trace. Bilinearity is inherited from matrix multiplication and the trace, both linear. For symmetry, the trace of A transpose B equals the trace of B transpose A, because a matrix and its transpose have the same trace. So the first two axioms hold. Now the heart of it. A paired with itself is the trace of A transpose A, and that trace is exactly the sum of the squares of all the entries of A. Write it out, and you'll see every diagonal entry of A transpose A is a column's worth of squares. A sum of squares is never negative, and it's zero only when every entry is zero, that is, only for the zero matrix. Positive definiteness, done. So the induced norm is just the square root of the sum of the squared entries, the Frobenius norm. For our matrix, 1, 4, 0, 9, summing to 14, so the norm is root 14. All three axioms hold. The trace form is a genuine scalar product on the space of matrices. Same three rules, a completely different kind of vector. Problem 8. Push it further. The vectors are now functions, paired by the integral of their product over -1 to 1. Find the length of f of x equals x, and show that x and x squared are orthogonal. Pause and try. The scalar product of two functions is the integral of their product. Length and angle come from exactly the same definitions, just with an integral instead of a sum. For f of x equals x, the norm squared is the integral of x squared from -1 to 1. Antiderivative x cubed over 3, evaluated at the endpoints. A third minus a third, 2/3. So the length of the function x, in this product, is the square root of 2/3. The blue shaded region is that function. Its norm packages the area of its square. Now orthogonality. Pair f equals x with g equals x squared. The integral of x times x squared, which is the integral of x cubed. X cubed is an odd function, and integrating an odd function over a symmetric interval gives 0. The antiderivative x to the fourth over 4 takes the same value at both ends, 0. So x and x squared are orthogonal, perpendicular functions, even though nothing about them looks like a right angle. Problem 9, the complex case. On complex vectors, the product conjugates the first slot. That's what keeps lengths real. Compute the product of x and y, then x with itself, and the norm. Pause and try. The Hermitian product conjugates the first argument. So first write down x bar. Conjugate 1, I to get 1, minus I. Now the product of x and y, 1 times 1, plus minus I times 1, 1 minus I. A genuinely complex number. That's fine. The product of two different vectors is allowed to be complex. The important one is x with itself. 1 times 1, plus minus I times I. And minus I times I is minus I squared, which is plus 1. So the sum is 1 plus 1, 2. Look what the conjugate bought us. Even though the components were complex, the product of x with itself came out real and positive. That's no accident. It's forced, and we'll prove it in a moment. Because it's real and positive, the square root is an honest length. The norm of x is root 2. The conjugate in the first slot is exactly the repair that keeps complex lengths real. Problem 10. Back to the ordinary dot product. Two vectors. Find both lengths and the angle between them. Pause and try. Start with the one number everything hangs on, the dot product. 1 times 3 plus 2 times 1, 5. Now the two lengths, each the root of the sum of squared components. X has length root 5, y has length root 10. The angle comes from the defining relation. The dot product equals the product of the lengths times cosine theta. Solve for cosine, 5 over root 5 times root 10. Simplify. Root 5 times root 10 is root 50, which is 5 root 2. The 5's cancel, leaving cosine theta equals 1 over root 2. And 1 over root 2 is the cosine of 45 degrees. The angle is exactly 45 degrees, which you can read straight off the picture. Problem 11, a proof. Show, using only the axioms, that the scalar product of any vector with the zero vector is 0. Pause and try to structure it. The whole proof turns on one harmless trick. Write the zero vector as 0 plus 0. Nothing changes, but now the second slot is a sum. Apply bilinearity. The product splits over that sum. So the product of x with 0 equals itself plus itself. Name it, call the number a. We've shown it equals a plus a. Subtract it from both sides, and it is 0. Therefore, the product of x with the zero vector is 0 for every x. No components, no matrix, just the axioms. This, write 0 as 0 plus 0 move, is one you'll reuse constantly. Problem 12, the last one, a norm property. Prove that scaling a vector by alpha scales its length by the absolute value of alpha. Watch where the absolute value comes from. Pause and try. Work with the norm squared. It's cleaner because it's just the scalar product of alpha x with itself. Bilinearity lets you pull a scalar out of each slot. Alpha comes out of the first, alpha out of the second. Alpha times the product of x with itself, which is alpha squared times the norm of x squared. Now take the square root of both sides. The right-hand side becomes the square root of alpha squared times the norm of x. And here's the subtle point the exam rewards. The square root of alpha squared is not alpha, it's the absolute value of alpha. If alpha were negative, alpha itself would be negative, but a length can't be. So the norm of alpha x is the absolute value of alpha times the norm of x. Doubling the arrow doubles its length. Flipping its sign leaves the length unchanged. That's the whole toolkit for the scalar product and the norm. Notice the reflexes we kept using. The 3-axiom check, 2 ways to test positive definiteness, completing the square, and the faster Hurwitz minors. Always naming a witness when the answer is no, recognizing scalar products on matrices and functions and complex vectors, and letting bilinearity carry the proofs. Master these 12, and this topic is genuinely done. If it helped, give it a like, and tell me in the comments which problem you'd like slowed down. You can support the channel on Patreon, link below. Thanks for watching. I'll see you in the next set.